Hello, friends. Welcome. Today, we shall take up the transient analysis. The transient analysis of DC motor. And we will consider there the separately excited variety. We know in analysis there are two types. One is the steady state analysis, another is the transient analysis. Steady state analysis is the one wherein the current doesn't change quickly, whereas transient analysis is the one wherein the current changes quickly. The time is important here. This rate of change of current, accordingly, the rate of change of speed, these two, the rates, they matter. They decide whether the operation is steady state or transient. Please watch. I am not referring to change in the parameter. I am referring to rate of change of parameter. So keeping that in mind, we will look at a separately excited motor and the equivalent circuit of that. Till now, we have done steady state analysis. For that, we considered the equivalent circuit of the separately excited DC motor. What all we had in steady state situation? We had field on one side, the armature on the other side. The field we showed with a coil with a resistance, and then the armature we showed with armature resistance, the back EMF there EB, along with that the supply voltage. I repeat, armature we had supply voltage, we had armature resistance, we had EB back EMF in the armature, whereas in the field coil we had field circuit, we had supply voltage, and field coil having a resistance, maybe we can call it as RF. Are you watching carefully the parameters I am mentioning? There I mentioned only R, RA here, R, RF here on the field side. I did not mention the inductance because that time the analysis was steady state. If the situation is transient, then the changes are very fast. When those changes are there, the inductance comes into picture. We know the basic concept of inductance. What is inductance ultimately? Inductance is an effect. It is not a physical reality. It makes its presence felt whenever there is a change. So when the current changes, inductance comes into picture. Now, keeping that in mind, we will look at the equivalent circuit of separately excited motor, DC motor. How does it look like? See here, we have armature, we have field. The armature is having the voltage applied to the armature. We can call it as VA. And in the armature, we have armature resistance as earlier, but now we are showing LA also, armature inductance also, and as usual EB we are having, and these being the electrical parameters, we have the mechanical parameters, the armature running at a speed omega m with a torque T. This is the equivalent circuit of the armature. What is to be noted is the presence of LA now. Similarly, on the field side, it is separately excited. We have the supply voltage to the field VF and field resistance RF. and the inductance of this field coil LF. Watch the equivalent circuit. Okay, next, keeping this equivalent circuit in mind, now for this circuit we can write KVL. Now the analysis follows a standard approach. We write KVL and we will link the electrical parameters with the mechanical parameters, and then we will arrive at a final equation. So I can write KVL for this. What that KVL will look like? Tell me. VA equal to IARA plus LA DIA by DT plus EB. Am I right? VF equal to IF into RF, LF into DIF by DT. That is the equation for the field. So we can write the KVL equations for the armature and the field as, can you see here? This is VA equal to IARA plus LA DIA by DT plus EB, equation 1. Here, so did you observe this? EB equal to KE pi omega m. You remember we wrote this equation? Back EMF is equal to, it's a function of flux, it's a function of speed. This is the proportionality constant. You remember that when we discussed about the fundamentals of DC motor, we came across this equation. So EB we can write like this also, KE pi omega m. And then VF, IF RF plus LF DIF by DT. Okay, I will take this as equation 1. I will take this as equation 1. So we have written the KVL equations for armature and then the field. Now we know that in the case of this DC motor, the torque can be represented in terms of flux, current, speed, and the equation is KE pi IA omega m. We have come across this equation also, if you remember. So torque is KE pi IA omega m. I will take this as equation 2. We have voltage equation for the armature. We have torque equation. Voltage equation is electrical equation. Torque equation is mechanical equation. So the motor is electromechanical device. It has electrical parameters as well as mechanical parameters. Please keep that in mind. So now after this, we know that the motor is what type of motor we have assumed? Separately excited motor we have assumed. Separately excited motor, the flux remains constant. That is why that Ke into pi I can take as a constant. I can put it as K. The equation becomes very simple. So keeping that in mind, we will proceed. Here I mentioned this is the torque, torque generated. That torque we can represent in simple in this fashion. Again, this equation also we have come across when we discussed about, where we discussed about this. Try to recollect this torque. I will give a moment for you to recollect. Torque we came across, where we came across this? When we discussed about components of torque, friction torque, viscous torque, useful load torque. You remember that? There we came across this. Ultimately we came to this equation. So torque is equal to TL, useful torque, B omega m plus J d omega m by dt. This is the torque equation. I will call this as equation 3. Now, using these equations, the equations that we have come across here, these equations, so we can now put, after differentiating, like this, equation 4. It's bit of mathematics. I will not go into the details. What I'm doing here is, I will substitute for this. I will bring in t, and then I will neglecting this part, that is this part. So with that, now I will bring in t here. How do I bring in t here? T is this, and in EB this is there na. I will substitute for this in terms of t. There is ke pi omega m. There is ke pi omega m. It will be t by ia, and then I will differentiate and then simplify. When I do that, then I will get the equation like this, and it will be really a big equation. We can simplify it by using these abbreviations: tau a, tau m, tau m, tau m1, tau m2. They happen to be time constants. One is the electrical time constant, the others are the mechanical time constants. So we get equation 4. Equation 4 is actually the equation linking electrical and then mechanical parameters. We have load torque here, we have d theta by dt, rate of change of position angle, nothing but the acceleration or the deceleration, and then we have rate of change of current. Okay, so now using this equation, which is a transient equation, we can realize any transient behavior that is expected. We can realize to get a particular d theta by dt. How much di by dt I have to have? To have that much of di by dt, how much voltage I should apply and over how much time, how I should increase that. That way I can link it with the control. So this is the transient equation representing the separately excited DC motor, wherein we have electrical and mechanical parameters both. Okay, so that's regarding the transient performance. Next, we shall move on to one more topic here, that is determining the energy loss during transient operation. The transient operation can be an operation wherein either we increase the speed or we decrease the speed. It can be starting, it can be stopping. So how we can determine the amount of energy lost during that event? For this, again, I take the equation for the voltage. We have already come across this. VA IARA plus LA DIA by dt Ke pi omega m. It's a transient situation. That's why L is coming into picture. Now, if I multiply on both the sides by IA, what it will be? VA IA equal to IA square RA plus LA IA DIA by dt plus KE pi IA omega m. I am just multiplying it by IA. Equation 1 is a voltage equation. I am multiplying it by current. When I multiply voltage by current, the parameters will become power parameters. Hence, equation 2 is a power equation. What does it convey? It conveys the composition of the power to the armature. We are feeding some power to the armature, na? The amount of power I am feeding is VA into IA, and that has different components. One component will be lost as I square R loss. Another component is electromagnetic power component. The third component is the one wherein mechanical parameter comes into picture. That is, this is the one which is converted into mechanical power. So the equation 2, what I am having here, in this Ke by Ia, we already know that it is T, the torque. The torque, it had 3 terms, no? Approximately it can be put as a TL plus J d omega m by dt, because normally that third component is lesser in magnitude. And in this, the electromagnetic power component is less relatively. Hence, we can put this as VAIA, this VAIA equal to IA square RA. I am neglecting this component. Then I will come to Ke pi Ia omega m. Ke pi Ia is T, which I have taken as TL plus J d omega m by dt. Hence this will become TL omega m, and then J d omega m by dt into omega m. J omega m d omega m by dt. So substituting for this in this equation and neglecting this, we will get equation 3. Equation 3 is actually the power equation, linking the electrical and then mechanical parameters. Now the total energy for the transient operation. We have some duration, some interval over which the transient operation takes place. In that period, in that interval, what is the amount of energy lost? We can find by using this equation 3. So this is the power equation. If we add the time component to this, this will become the energy. Watt into second, joule, watt power, watt into second, joule energy. So what we will do, we integrate this equation 3 with respect to T to get energy. So we get energy by integrating equation 3. What we will get? VIA, integration VIA, it is dt, VIA dt is equal to IA square RA dt, integration of this, TL omega m dt, J omega m dm by dt into dt, it will be only d omega m integration. Nothing but we are bringing in the time component into this. And that's how we get equation 4. Equation 4 is the energy equation. Energy during the transient operation. Please keep that in mind. Now, from this equation 4, from this equation 4, we can get what is the energy lost. This is the total energy. We are feeding so much of energy to the armature. Out of that, some amount will be lost, some amount will be stored in the electromagnetic field, some amount will be converted into mechanical power, which we are actually using for something useful application. So what is the loss here? Loss is this. Hence, from equation 4, we can get the energy lost as this component, that term I am writing here, equal to this term minus these two, minus TL omega m by dt with TL omega m into dt minus j omega m d omega m. I repeat, IA square RA dt integration is the energy lost equal to this minus this minus this. That's what we are having as equation 5. So equation 5 is the equation for the energy lost. Equation for the energy lost. Equation 5 is the energy for the equation for the energy lost during transient operation. So from this equation, the equation 5, we can get how much is the energy lost in different situations depending on the type of transient operation, be it starting, be it stopping, acceleration or deceleration. Considering those cases, we can find how much is the loss. Only thing is, considering the transient situation, there we should substitute proper limits, the integration limits. From what to what? If it is time, from what time to what time? If it is speed, from what speed to what speed? If we substitute properly, then we get the energy lost. Now I will give the results of one or two examples. If we consider the transient operation of starting, wherein the motor is started from rest and is going up to the rated speed, nothing but the speed changes from 0 to rated value omega m. So if we substitute that rated value to omega m, then how much will be the energy lost? Energy loss, simplifying that equation 5, we will get it as half j omega m square. Similarly, if we consider the braking event, dynamic braking, wherein all the energy is lost in the motor itself, dynamic braking, rheostatic braking, you remember the types of braking we discussed. The speed is brought from the rated value to 0, it is stopped, then we get the energy lost, the total energy loss as 1 by 2 j omega m square. Whereas if we consider another type of braking, that is plugging or the reverse current braking, then the energy loss is more than this. It is 3 by 2 j omega m square. In these situations, in the case of dynamic braking, the lost energy is half j omega m square, whereas in the case of reverse current braking, energy loss is more. You remember we made this statement when we discussed about the braking methods. Then we mentioned that the plugging is the method wherein the energy loss is more. That was the demerit. That's how we mentioned. Of course, we also mentioned that plugging merit as it is the fastest method of braking. So in the case of plugging, reverse current braking, energy loss is maximum, but it is the fastest. The higher deceleration, the quicker braking we are getting at the cost of higher loss. Is it okay? So that's how we can calculate the amount of energy lost during the transient operation. Okay, so with that we come to the end of the transient analysis. We have made a reference to the transient analysis in a very brief manner. With that, we are coming to the end of this unit, DC drives. We shall stop there. We will continue our discussion in the next class. Bye. Take care.